Good afternoon, everyone. Thanks for joining us for today's presentation. Probably many of you know Xiaodong, but I do the introduction now and then can start this presentation. So Xiaodong Li is a professor in AI with the School of Computing and Computing Technology at RMIT. He holds a PhD in AI from University of Otago in New Zealand. His research interests includes different aspects of optimization like multi-objective, multimodal, large-scale, combinatorial, as well as evolutionary computation, meta-heuristic, and swarm intelligence. He also has interest in machine learning, data mining, deep learning too. He is the recipient of 2013 ACM SIG Evo Impact Award and 2017 IEEE Computational Intelligence Society for Best Outstanding Paper for the IEEE transaction on evolutionary computation. His publication has received more than 17K citations, and his H-index is 62. He's an IEEE fellow and IEEE CIS for Computational Intelligence Society Distinguished Lecturer. He also served as a member of ARC College of Experts. He is now part of that College of Experts since 2023. And earlier this year, he was the chair for GECO conference as well in Melbourne. And in the past few years, he has dedicated most of his research effort in developing innovative machine learning techniques for solving large-scale combinatorial optimization problem, which I believe he will talk about this topic today. And so welcome, Xiaodong, and over to you.
Thank you, Hardy, for the kind introduction. Yes, as you said last, it's sort of a, topic I'm going to talk about today is the thing that we've been working on in the last few years, as you can see on the title, solution prediction, machine learning, especially for handling large-scale combinatorial optimization. I believe Dr. Yuansen had this talk 3 years ago. That's actually we had a few publications because at that time, but the 3 years passed. We have done quite a bit more along this line of research. So hopefully, by the end of this talk, you get a glimpse of what we have achieved in the last few years in this particular area. Yeah. Okay. So this is just an outline of the talk. So I'll give you just a quick general background on large-scale combinatorial optimization, why machine learning can play a big role here. And there are a few things we have done in the last few years, and especially we use this technique we call solution prediction for the purpose of problem reduction. As you know, the large-scale problem, the size of the problem is a key barrier, and how we can either decompose a problem or reduce the problem size, and so that you can let some of the existing method can become effective again. So I'm going to use, there's a few things I want to show in this talk. Probably not going to go into too much detail, but hopefully you get a glimpse of, what can be done by using machine learning for some of this decision-making point for combinatorial optimization. First, I will use this maximum weight clique problem as an example to illustrate, how this concept works. Then I'll go on to talk about, generalization. You can use machine learning to learn from the problem instance. Then you can apply to problem of a similar instance of the similar characteristic, like this TSP problem, right? So can you learn and train on one type of TSP problem, traveling salesman problem, but generalize on some variation of traveling salesman problem. And the technique you can also be generally applicable as a warm start procedure for See here the example, we're using ACO to warm start ACO, but essentially you can use to warm start, any other type of optimization method, especially if, instead of a cool start, you have a warm start. So you're in a better position right from the beginning. So then I will introduce this kind of a pricing heuristic. We can use machine learning to replace a pricing heuristic in the context of this column generation. Right, so you can replacing some of this pricing heuristic. So by using machine learning to make a prediction what column to be bringing to the restrict master problem. Therefore, you can achieve efficiency, not just efficient, but also better result in some situation. And the last one, or the example of we can learn directly from high quality column. If you have a way of characterizing the high quality column, like a decision variable, then you can learn directly instead of learning the relaxed problem. Now, one most recent kind of thing that we have done is to make this solution prediction technique more adaptive. So you can, in fact, further fine-tune the statistical feature using what we call this adaptive solution prediction. And I also touch on the ASP, so adaptive solution prediction technique, is relationship with this EDA. So this is some of the examples, large-scale combinatorial optimization, the vehicle routing, beam packing. I think I don't have to say too much. You all can see they are kind of quite a practical problem, have lots of constraint, but you can also capture a lot of data for this problem solve if you already have some problem instance to solve it, right? So this is a example in the Australian context, constraint pits problem in mining. So we talk about very large scale. So imagine you have this the pits, right? And you want to figure out where the mineral lying underneath the ground, and you might get doing some drilling, getting some data out, then construct your model, then perhaps construct this model. But the typical model for this type of problem, you're using a variable to, let's say, each block of this cubic block of this dirt will be defined as a variable. So you could end up with a million of decision variable for typical this type of modeling. So therefore, for conventional optimization method, whether it's like a CPLEX and the standard MIP solver, or a meta-heuristic, it's just impossible to deal with it. It's just too big to handle. So for problem like this is a large one. We're talking about 96,000 of blocks. So that's number of decision variable, and a precedence, that's a constraint. You have a huge number of constraints as well. And we talk about the last instance, there's actually over about 3 million of variable and 34 million of constraints. So they are humongous. It's impossible to tackle directly. So we have to look at other ways of either decompose a problem or doing some kind of a problem reduction. And that's what we're hitting, try to do problem reduction. And this is just another example for traveling salesman problem. As you can see, so the number, the city we have here in this case is 13,000, right? So this is the US map. And the one thing you notice that the solution, in the edge in the final solution is actually probably take up less than 1% of all the edge, the possible edge that connecting all these cities. So the solution is very sparse. So whether we want to start, searching, optimizing a problem from all the possible edge that you have at the start, or you can look at other ways. Perhaps you can prune the search space so that your search effort can be more concentrated on searching a prune search space. So this is actually inspired, I guess, motivate us why we need to do problem reduction, because we observe the number of edge in the final optimal solution only account for, in this case, it's very sparse, less than 1%. So the other thing I guess motivate us to do is, again, because the data are abundant these days. The data are available because the sensor technology. And so you have let's say you have a pizza delivery service in Melbourne CBD, and you can have the company collect the data from the previous tour, right, delivering pizzas around CBD. The data can be collected, and then that provide the foundation for you to do this training of your model, machine learning model, right? So at the same time, you notice many optimization algorithms that require handcraft heuristic, the classic mid-solver, CPLEX, Gurobi, they're still using sort of a heuristic based on just human expertise or knowledge you accumulate over the years. But every problem is different. Therefore, handcraft heuristic might work for one situation, but not necessarily for some other situation. So whether we can learn from the data, therefore reduce kind of this repetitive process every time you have to develop your solution from scratch. And that's what we try to look into. Yeah. So we really got a lot of this kind of a idea, feel really inspired by this particular paper by Benjo, Lodi, and Purvis in 2021, Journal paper, survey paper. So some of the idea here really, you can see provide the possibility that you can try to bring in machine learning technique to enhance all these potential decision point that when you do a classic optimization, like here you see on the right, this branch and bound procedure, you have to consider which variable to select, right, on which node to expand. These are we consider the decision point, right? So to make this decision, people tend to use heuristic, but can we use machine learning to learn from previous collected data that they already have some success and knowing for a particular situation, you should go this way, pick this variable or this node to expand. And so if you can collect enough data and you can learn from the data using machine learning model, right? So that's really what we try to look into. So as you can see here, I list some possibilities here, like a branch and cut, how we can generate a cutting plan intelligently. Right now, the cutting plan method just generate lots of cut without considering, whether they're efficient or not. So some of the cut are maybe just a waste of computational resource. Can we do a much more intelligent, smart way of doing this to save the computation cost and actually do better cut, right? All this learn by demonstration, that learn from the expert. So if you have data collected, label data, so this is in fact supervised learning, then we can learn from the data so that, next time you encounter similar situation, you know where it's heading, right? Or learn by experience, so that represent this reinforcement learning. So you learn on the go, you're collecting data and learn interactively with the environment or other agents, but you don't necessarily have a fixed goal at the beginning, but you kind of are getting this reward, but accumulate the award. Your goal is to have long-term, accumulate reward, maximize that. All this automatic parameter tuning instead of have manual tuning, right? So in this particular case, we're looking at problem reduction. How can we, because we were thinking about how we can better tackle large-scale combinatorial optimization. So you have a lot of vertex here, as you can see here on the left, and a lot of edge and connections. So if you can do this problem reduction, something like transform the graph from the left and to the right, you can see you can prune the search space significantly. Of course, you're not going to do them randomly. So what we hope to achieve here is to prune the space in a way that will keep the edge in the optimal solution, and so that the edge and vertex, so that in the end, when you do optimization on this simpler and smaller smaller size problem, eventually that's equivalent to achieving the optimization of the original much larger problem, right? So that's what we try to do. It's a kind of a generic technique. You can consider some kind of pre-processing step for any kind of a large-scale combinatorial optimization. So first thing you would consider is to do the problem reduction, normal optimization, but we try to reduce the problem size. That's what we try to focus on. Once the problem reduced, and we want to reduce in a way that we want to maintain those component that is highly likely to appear in the final optimal solution. Therefore, when you have this smaller search space, you can still have a reasonable confidence to obtain the optimal solution in the end. So first you do the problem reduction, then you apply some generic problem solver, exact solver, or heuristic method, meta-heuristic method to solve the problem, right? So this is a very generic approach we are talking about here. Problem reduction is, we're not the first one. There are people already done it in the past, like based on using exact approach. So the advantage, they have this optimality guarantee, but it's not necessarily it's achievable in practical problem solving because the efficiency issue. On the other hand, the heuristic approach tend to be very efficient, but it's no guarantee of optimality. So there's a kind of a give and take there. So just give you a general idea what we try to achieve by using this graph here. So you can think about, like for traveling salesman, we have some problem instance already solved. Here the orange edge is we know that appear in the optimal solution. So we can characterize this edge using giving them features, defining them with features, right? So you can draw them on the feature space. Therefore, you can transform them into a like machine learning problem. Here, what you try to learn is to separate the dots, right? The orange dots from the blue dot. The blue dot is the edge is never appear, highly unlikely to appear in the final optimal solution. Since you have this problem instance solved, so you know the label of it. So it's like a supervised binary supervised learning problem. So what you try to learn here from the data is to use a machine learning model to learn the decision boundaries. Here it's just showing a very simple way, just a linear function to separate this the orange dot from the blue dot. So optimal zone from non-optimal zone. Of course, you're not necessarily doing a perfect job, but even you do a reasonably good job, there's a lot of this edge can be pruned away. You have high confidence they're not going to appear in the final high quality solution. Therefore, you can prune them away. So the upper part of this graph showing, well, this is what we try to do, the training part. The bottom half of this graph is where we try to make a prediction on the unseen test instance of a new graph, a new traveling salesman problem, for example. Then we'll also, of course, characterize those edges. The edges will be, you make a prediction based on the edge value, the feature defining this. Then if it appears on the, let's say, the top right corner, above this boundary, decision boundary, then they have a high probability being going to appear in a final optimal solution. Whereas the low quality solution region, is the bottom left corner. So by doing this, then you can really prune away those edge that appear in the low quality region, as you see here. And this is how we achieve the pruning of the search space. So once the search space is pruned, and you can do your optimization, the generic, optimization on a smaller size problem, and in order to find optimal solution. Okay. Yeah. So the traditional methods tend to do this manually, but now there are more and more growing interest that people try to use machine learning to do this. The advantage is you can automate the design optimization technique, right? So rather than every specific application, you have to do them differently. Here, you can learn from the data. The key thing is you have the data available. So this in the red box is pretty much capture in plain English language the general procedure you follow for this solution prediction using machine learning for problem reduction, right? You solve set of easy problem instance to optimality that give you the label information. Then you can construct your training data set. based on these instances. So the instance in the previous slide, as you can see, the training instance is really just an edge. Like sometimes we use a vertex, sometimes we use an edge, and whatever feature you define for vertex, right, that can be you can gather all those information. So of course, for machine learning, you have to define those features to characterize those decision variables, whether it's edge or the vertex, right? So once you have this label data, then you can do your training. The goal is to separate the optimal solution from the non-optimal solution. So we're treating them in this case just a binary classification problem. Then once you've done that, you can remove those variables that is appear in the optimal, non-optimal region, therefore achieve the search space pruning, then apply this in unseen data, to predict on the unseen graph the edge, whether it's highly likely appear in the final solution or not. Okay, so a simple example here, this maximum weight clique problem. This is a typical graph problem, classic one. As you can see, the graph on the right. So each vertex, they have this index and the weight. So the goal here, the maximum weight clique problem, is to try to find a subgraph. They all need to be connected, all the vertex. Then the maximum amount of this, the weight with the maximum amount of weight. So you want to find, the problem is to try to find the subset of this vertex that are all connected and have maximum amount of weight. So that's what you try to achieve. So we can, here, two features you can think about. If you're using, you try to characterize the vertex. For example, the degree of the vertex. The higher degree, more likely that appear in the maximum clique. All the weight, the higher the weight, the better. So the feature definitely carries some information that you can learn from, so that to figure out in the end by the machine learning model whether that vertex is highly likely to appear to the final optimal solution. So once you have this feature defined, so then you solve this few simple instances, this maximum weight clique problem, then I can do this plot of features. In this case, I'm just using an example. We have two features. There's no degree and no weight, right? And you have you can see that the very few red dots that represent those vertex that appear in the final optimal solution from the solved instance, whereas the majority of the dot is actually gray, that they do not appear in the final optimal solution. So now we can use machine learning model to separate these two groups. We can use a linear function, do a first cut. You can do, if you can prune away the bottom half of these dots, right? That means you have 80% reduction on the size of the problem, right? So you can do even better with a decision tree. So you have a more elaborate staircase boundary, in this case, decision boundary. So you can achieve further reduction. So now at 88%. Of course, you can introduce more features. So the feature about the problem itself, the graph itself, like the vertex, all the weight, all the edge sometimes. So in this case, it's the vertex weight and the vertex degree. And you can also have feature defined from the mathematical formulation, like the objective bound, like the maximum amount of weight the vertex accumulated with the vertex under consideration and its neighbors. All the features from MIP formulation, all the features from LP relaxation. So one type of feature we could particularly considering in our research is this is statistical feature, which is using sampling. So if you have a set of feasible solution provided, you have a pool of a feasible solution, and I can do sampling to extract useful information for me to identify the vertex that is highly correlated with the optimal solution, right? So this is also quite a effective way of defining feature. So here's the example, we talk about this statistical feature. So we have algorithm already developed that is, you can generate lots of feasible, not necessarily the the optimal solution, but it's high quality solution. Therefore, you can do sampling. So through sampling, and you can then we use these two features, two statistical features. One we call ranking base. Basically, the idea is similar. You try to identify those vertex that is highly correlated to the high quality solution or the optimal solution. So we call them high quality because they share, we call them backbone with optimal solution. So they are the vertex frequently appear in optimal solution given the data that you have collected that demonstrate that, right? And so the other one we're using is a Pearson correlation. So both of them have similar idea to calculate, to obtain that high correlation information between the vertex and the high quality solution. So if you include more feature, I guess one thing nice about machine learning, you actually include several different more feature quite easily. One, it doesn't hurt. Even the feature maybe just play a very trivial role. So if you include more feature, you likely perhaps have a slightly better performance. In this case, we can show that if you have more features, then I can have even more further the problem reduction achieved without sacrificing the optimal solution, right? So this is showing if I have a more feature, then I can project all these to using PCA. Then we demonstrate on these two first and the second principal components, and that's what you see in the feature space, right? Of course, training should not be confined just using one graph. So we're looking at using here, we're using 26 graph from the DIMAC library. So that's a lot more than one graph that you can gather your label data doing the supervised learning. And the number of nodes here we considered is ranging from 100 to 1,500. The number of edge for this type of graph could be up to 500,000. Yeah. So this is just showing this the two principal component, the space that you can get the sense of where the point. You can see the red point represent those vertex that appear in the final optimal solution. Right, so then you can using the typical machine learning training procedure, leave one out using some of this, in this case, some of the medium-sized graph for training and reserving one for testing. But just note that the training instead we're talking about is just a vertex, right? It's not a whole graph. It's not a graph. Therefore, you do have a very large training data set. In this case, could be few thousand up to millions. Yeah. And you can try different machine learning model, support vector machine, decision tree, nearest neighbor, neural network, even more recent ones like a graph neural network. And here is the one we're showing you. We're using support vector machine. And you can see the red dot on the right hand side. They are concentrated on there. So we try to find a decision boundary that is separate the grid out from the red. Of course, you cannot do a perfect job. And that is understandable. This is really, I guess, an imbalance problem. You have more point that is appear in the non-suboptimal solution, right? A non-optimal solution, whereas a few edge that appear in the optimal solution, like we mentioned earlier for the very large scale TSP problem. So it's you want to penalize particularly those if you have a misclassification of edge of a vertex appearing in the optimal solution. So the misclassification should have a high penalty, whereas if you have a non-optimal solution classified incorrectly, this actually doesn't really matter much. You include them, it's just that the pruning might not be you have one more size in terms of the edge. So it's not as efficient, but at least that's not a critical issue. But if you miss a vertex in the optimal solution and not going to be really severely impact on the performance, you might end up having just a suboptimal solution. So here's the summary result. We show that is we can see the purple one showing we're combining all the machine learning feature. You have the best performance as you do the problem reduction. So if you look at the last graph, this L14, if the reduction is severe, and the machine learning performance actually reasonably well. Whereas using single feature like just the weight as a feature, the performance degrading very rapidly. Yeah. So basically it shows that if you're using machine learning combine multiple feature, that tend to do better than just considering just one feature. Yeah. So then we test our method on very large and hard graph from this website network repository. You have 11 graph. Then they have, the nodes of the graph is over 600,000 edges, 200 million, and there's a clear evidence of performance gain that you can obtain by doing first with problem reduction. If you do not do problem reduction, you tend to have, this gap, falling behind. So it's just showing the effect of the problem reduction can play a very important role in getting better quality solution. And the next idea we try is a generalization. So we want to see whether if we train model on one type of traveling salesman, can what the machine learning model generalize on a different category of traveling salesman problem. So we borrow some of this, we look at this Matilda library, which is proposed by Kate. And here we're showing that I think there are 7 different categories of traveling salesmen, but we only use 5. So the first one is CLK easy. So the traveling salesman in this L1 category is easy for CLK algorithm, or CLK hard, or LK CC easy or hard, right? The last one is random. So you can see the color. It's just showing. If you plot them in the feature space, it's showing them in they locate in a different region, right? So they have a different characteristic, and they have a different they appear in a different places. Yeah. So then in this case, we train our machine learning model using CLK easy, and to see how well it generalized on including CLK easy, but also on other category. So you can see if you're showing this blue color, that means the optimality gap is close to 0. So definitely it generalizes really well on the same category, CLK easy, but we will struggle to generalize on some other category of problem. Like you can see on the right-hand side, they all appear with much higher, this different color, which indicate they have a much larger optimality gap. So then next thing we tried is to train using much harder instance, the CLK card, then see whether they can generalize on easy problem, but also on some other category of the problem, and shows a much better generalization across the board. So in this case, you can see most of my blue color. And also demonstrate by the figure, you can see we can achieve 78% the edge removal or pruning with optimality gap around 0.07%. Right. And if then the next thing we tried is on the random graph, and surprisingly, it actually also worked quite well. It achieved this 85% pruning, still maintain the average optimality gap of 0.4%. You can see on most the category it do well, although there's a few higher optimality gap for some of the category, but generally speaking, on the whole, it performed reasonably well. And we also test on the generalization capability of the machine learning model on if we train problem with smaller size, see how well it can generalize on larger problem size. So we train, in this case, using this random category I7 problem instance of 100 dimension for training. Then we tested it on problem with much larger instance, or probably the same way of generating them. Like say this random category, but it's of different problem size. You have 200 city, 500, up to 2000 city. So the graph on the right showing that we can still achieve pruning with to almost close to 90%, we're retaining the optimal solution. So it just shows the effect of generalization can be achieved here as well across problem size, right? If different problem size. We also look at how we can use this machine learning technique as a warm start technique. So for ACO, generally you will start a random refinement matrix, right? So this is the equation you can see on the screen. You have this tau is a refinement matrix. You have the heuristic weight matrix. So generally they get initialized with random value. Then you then you construct refining your refinement matrix over iterations, and then that's how you achieve in the end maybe found the shortest path. But we can, if you have the data that is showing the problem from the solved instance of problem, in this case, we're using this orienteering problem, which is a variant of the standard traveling salesman. And you can actually construct your machine learning model, construct your training data to train the machine learning model to learn from the label data what edge that appear highly likely to appear in the final optimal solution. Therefore, instead of using this random tau or eta here, refinement matrix or heuristic weight, we can inject with this sort of a probabilistic model, right? So this is really the key idea. So we can use a whole set of features. I'm not going to go into detail because given the time. But most important, you can see we also have the statistical feature using random sampling apart from the general feature describing the edge. So you do the same thing. You train the model with the label data. Then you try to identify, learn the decision boundary. Once that's learned, then you can make a prediction on unseen graph. Then identify the edges that belong highly likely to belong to the optimal solution or not, then do the pruning, as you can see here. Right. So we have three variants in this particular case. We replace the eta, which is the heuristic weight matrix, with a probability our probability model learned from machine learning, right? Or the other variant we have is eta with p, but also another heuristic that we borrowed from again this commonly used heuristic, this Sj divided by Cij, that is also used for heuristic. If you combine the two, perhaps you can do even better. Then the last one we try is just replacing the tau, which is a refinement matrix, with the probabilistic model that we have learned. So you can see from this graph showing, even from the very beginning, first iteration, if you're using standard ACO, the randomly generated solution that appear, this objective value has been normalized. So they are very low, the objective value. But if you're using machine learning to do a warm start, even right from the first iteration, you have a much better position. So the best one is this SVM ACO eta hat. Eta hat is the one using heuristic weight plus the additional heuristic that we added combined. So as you can see here, the second one. And these have the best performance. So you right from the beginning, because you have used machine learning to learn from the data, you can start in a far better position than if you're not using such a warm start procedure. As you can see here, the machine learning model also with this eta hat variant perform the best. For these two graphs showing, one we're using this is more greedy approach of ant colony, the other is less greedy, and the greedy one show even better performance. So you can train your model and using again on a different problem size. We look at that synthetic data, demonstrate this generalization capability across two different versions of this ant colony algorithm, classic ant colony MMAS and MMAS, right? So this is a more greedy version. And greedy version again showing better performance than the non-greedy ones. And we also look at whether we can generalize what we learn from synthetic to real world problem, and this is a result that's showing that's indeed the case. So what you learn even with the synthetic data, there's something that is transcend, right? That also that can be used for real world, like a similar to a traveling salesman, but might not be exactly the same, but a lot of things that they share that they in common that can be learned from this procedure. So next thing we try to look at column generation, because a lot of this large-scale combinatorial can be formulated with Dunsey-Wolf reformulation. So in a sense, a typical procedure for solving that is apply this branch and price, and then the leave for this branch and cut procedure. At the leaf nodes, you apply what we call column generation. This whole thing we call them branch and price. So for column generation, essentially you have a large scale LP relaxation problem you try to tackle. The number of variables is exceedingly large. So what you normally start with is the restricted master problem. It just take a subset of the column. Then you solve that restricted master problem. The primal, then you can using the dual of that to generate the formulation for the pricing problem at that particular iteration, then solve the pricing problem. Then from there, you identify the most negatively reduced cost column, and that's a column you're going to add back to the restricted master problem. And so it goes. So you're going through many iterations, and that's how you add more column to the restricted master problem until you have no reduced cost below 0, right? So that's you found the optimal solution. So this is what we consider there's a bottleneck here because it's pricing problem. You have to solve them every iteration, and every time you only can add one column. So if I can replace this pricing heuristic with machine learning, essentially I can gather more information. I can actually add more than one column into restricted master problem. Therefore, will be more efficient. So that's what we try to do here, right? And we apply in this case to this graph coloring problem. As you can see, the pricing problem here is a max weight independent set problem. And from literature, you can see they're using standard solver to solve it, and including ACO. And here we just try to compare our machine learning approach with all these classic methods in the literature. So this graph showing typically still the as you seen early on, you have label data. You have some problem instance to solve a graph coloring problem, the pricing problem. Then you construct your training data set. Then you do training. Once you have the training done, then you can go into this testing stage for a new graph coloring problem. Then when you at the time want to make a prediction on the pricing for the pricing, then you apply your machine learning algorithm. Then determine what edge should be included, right? As I said, the advantage of this is that you can have more than one this column to be selected from to add it to the restricted master problem. So here the column is really this maximum independent set that we're talking about. And we're showing that in our paper, you see the AAAI paper, there's the efficiency and also the quality of the solution that you can, these are the benefits that can be obtained. Yeah. So again, this just a detail about the how you gather the training data and use the training to construct your machine learning model. Given the time, I need to speed it up very quickly. So this is just some results showing this pricing. The machine learning model definitely have there are some edge over the existing method. So instead of learning for the pricing, we're also looking at can we learn directly from the column? Because ultimately you want to find integer solution for, like, say, a graph coloring problem, right? So if you can characterize the maximum independent set, which is the column that you're going to use added to the restrict master problem, you can learn directly from that. So yeah, it comes down to defining a set of features to characterize this maximum independent set. And you can learn using a machine learning model to learn directly from that. Then when the time comes, you using your model to predict what column is actually highly likely to belong to the optimal solution. In a sense, it's almost like you have a warm start procedure for the column generation. Instead of doing the standard column generation, select one column at a time based on negative reduced cost. Here you can start with the set of high quality solution right from the beginning. So in a sense, it's a warm start procedure as well. So can we even do better from this machine learning solution prediction? Can we characterize this decision variable more than just we gather from the historical data? So far we have learned, we have shown you here is model being trained offline. But you have new data might come in over time, even when you try to make a prediction of unseen instance. So that data there can be utilized to maybe refine your features. And that's what we try to do here, refining statistics, because for the statistical feature, we're using random sampling. So there further information can be obtained from newly obtained data. It's not necessary for training, but it's for fine-tuning the feature. Okay, so showing clearly in this graph. So in the testing stage, it's only in the testing stage, we added this procedure that iteratively to refine the statistical feature that we obtain from the high quality solution that is you can produce and generate it from the search method after you make the machine learning prediction. And we found that very, very effective. So I'll skip this. So this adaptive solution prediction, it has some similarity to this estimate distribution algorithm. In a sense, the EDA, you do this probabilistic modeling, you doing them iteratively. Every iteration, you will gather information, you make adjustment on the probabilistic distribution. For us, we train the model offline. So in a sense, we learn from the historical data without having to do this kind of alternating between learning and optimization. So therefore, it's kind of you learn, you train, pre-train them with the data you got. So you can start straight away at somewhere much better position than from a random initial population. So here just showing this effect of apply this adaptive solution prediction, using refined statistical feature. After a few iterations, you can see on the graph here, it have a much better separation from those edge belong to the optimal solution and those that do not belong to the optimal solution. So I've skipped this result because I'm conscious about the time. They just a further result that we it's in the paper that we mentioned there, comparing with some state-of-art models. This adaptive solution prediction method achieve some better performance on 3 types of problem. Here is the Maximum Weight Clique problem, also the TSP plus orienteering problem. And this is result on the branch and price. So on the branch and price, we group the problem instance differently. The first group was showing with machine learning definitely have upper hand. You have better solution, better solving time. But you look further down, group 2 is maybe mixed. It's not necessarily always the case. For some group 3 and 4, it's probably for this type of problem might not be necessary to use machine learning because the classic solver probably already have a very good way of solving it, like the pricing aspect of it. Right? So just quickly the summary. So you can see from the presentation that this sort of using machine learning and doing this supervised learning can be a very promising method for solving large-scale problem. In the sense that we use this to achieve problem reduction, right? It's a generic technique. It can be a plug-in to all different optimization projects as a pre-processing step, right? You do the problem size pruning first, then you try out your general solver or meta-heuristic and so on, right? And the advantage is that you're moving away from relying too much on this handcraft heuristic, and you can use machine learning to learn from historical data instead of, you know, every problem is different. You have to use a different heuristic. Here you can learn directly from the data. So the other kind of the standout feature is this a statistical feature that we use using random sampling, that we can fine tune the feature. You know, even in this adaptive solution prediction procedure, demonstrate that can be further provide further benefit to the problem solving process. Yeah. And just the last point, that is, you can see there's a synergy between meta-heuristic, mathematical programming and the machine learning. There's a lot of complementary kind of role that you can play from this different area of research. So maybe we can look into more in the future how we can actually tap into this synergy for come up with developing even more effective algorithm optimization method. So these are some of the publications in the last few years, and these are the people I would like to acknowledge. So we have this discovery grant in the 2018, especially Andre and Yuan Sun, Dr. Yuan Sun. We work closely on this project, plus some other PhD students and collaborators. Okay, thank you very much.